All right, so we're going to get into how we describe dissolving from a chemical equation point of view. So in understanding how solutions work, we're going to be looking at a solute like, say, sodium chloride. And to refresh your memory, a solute is anything that's being dissolved in a solvent. The solvent here, of course, is water. This is called the universal solvent, although it doesn't dissolve everything. It dissolves more than any other substance. And so the reaction is going to take place within this, what we call medium. The water is going to be the location where all the reaction is going to take place. So we're going to focus on the sodium chloride. NaCl, as you know, is a white crystalline solid. So when we write the chemical equation for anything, we're going to have to include the phase for this. We then draw the arrow to show that we're going to go from reactants to the products. Now, when we take the water and we collide with the clump of sodium, that's exactly what's going on here. We've got a clump of ions. We don't find sodium chloride in molecular form. We find it in ionic form. We talked about this a little bit before, but it bears repeating. Let me try that again because that was just awful what I just did. And so these large particles are the negative ions because they gain electrons, more electrons and protons, so they tend to expand. And the positive ions are the small particles, the sodium in this case, because they've lost in the outer level, which because they lost all the electrons in the outer level, the one electron they had, and now you have more protons than you have electrons, and it just kind of sucks it in there, but not completely because the other electrons are spinning around. So then water comes along. Now water is what we call a polar molecule, H2O, and has about 190.5 degree bond, although it's actually a little bit less, that's like 107. But the oxygen is electronegative, which means this is the negative side and this is the positive side. We call water a polar molecule. And the nice thing about polar molecules is that when it comes to a clump of ions like this, either part of the water can attach to this. And the collision is going to be violent enough that it's going to break the bonds, and then it's going to rip off whatever it is wanting to attach itself to. In the case of water, with the negative particle right here, it's going to go after that positive sodium. And it's going to collide, and it's going to bond to that part, and it's going to pull that away. And then water over here, which is polar, this is the positive side here, this is the negative side here. This is going to be attracted to the oxygen or not the oxygen, the chlorine and the sodium, because opposites attract. Collision, boom, attachment, yank it away. Okay? And actually there's 6 water molecules in each one of these ions that's being ripped apart. Because once this gets pulled off, other waters are going to join in the pulling this thing off. So, but when we show this, we don't show the water part of it as this part of the reaction. We put it as part of the phase. So in other words, we are going to get sodium attached to water. The sodium ion, which is Na positive, attached to water, the abbreviation we use for that is AQ, and that stands for aqueous, which means in water. And I talk about in the script that aqua is the Latin word for water. That's where we got agua from Spanish, and aqua or aqueous for chemistry. Then the chlorine becomes chloride ions. It's no longer pure chlorine. You don't want pure chlorine in your water anyway, unless it's small amounts. But even the stuff that you have in the pool is not pure chlorine. If it was, we'd all be dead from swimming in our swimming pools. And this is going to be aqueous. So this is the correct chemical equation describing the dissolving of sodium chloride. And it's all based upon this idea that the polar water, which is why it's such a good solvent, will attach to anything positive or negative. Okay? Now, that's one aspect of looking at this. Now, the other thing here, and I'll go back to the script here, and I'm talking about This is the equation that we're talking about here. And then we're doing the example, and this is right the dissolving reaction with the compound calcium iodate. Okay, so let's take a look at that. Calcium iodate is a solid. How do I know it's a solid? Because this is an ionic compound. How do I know it's an ionic compound? It has a metal. If the compound has a metal in it, it is ionic. If it is ionic, therefore it is a solid. We're going to dissolve this in water. Now, one thing I did not put up here, and I really need to get in the habit of doing, and you do too, is to show that water is indeed the medium here. So we'll put the H2O that is technically not part of the equation. It is simply describing the medium at which this separation takes place. Goes above the arrow. And then on the script, you'll see that it's each one of those arrows have an H2O above it. Same thing here. This is going to be the H2O water right here. Now, at this point, you're going to need your polyatomic ion chart and you're going to need your periodic chart. Now, the periodic chart is going to help you identify the charge of metal. So, calcium is a main group metal. And again, a main group metal means it's either in the first 2 columns or the right 6 columns. The transition metals, of course, are in the middle. We'll talk about that later on. Or we have talked about that, but anytime you come across that, remember you have to look at the polyatomic ion or the negative ion first, and then figure out the charge of your transition metal. But this is easy, because calcium is a main group metal. It is in group 2A, which means it has a positive 2 charge, because metals that are main group metals have charges that are the same column as the A column that it's found in. So this is 2A, so this is going to have a 2 positive charge. Now, the next one, you have to go to your polyatomic ion chart. I've included a link for that in your Google Classroom. And you will need to find IO3 in that polyatomic ion chart. And then you'll see that that is a charge of 1 negative, or negative 1. So that means then that the water is going to attach itself to 2 of these ions for every 1 of these calcium ions right here. And it's going to create an aqueous ion. So we're going to get calcium 2 positive aqueous. There's no subscript number for this, so we assume it's going to be 1 plus. Now, this is where it gets a little tricky. You've got to be careful with this. You have 2 iodates. The parenthesis is there in this compound to show that the charge is added to 0. But when the ions are by themselves, you do not need parentheses over here. So I'm going to put no parentheses. If I learn how to spell, of course. Parentheses, or parentheses, because that's the plural parenthesis. There's no parentheses for, shall we say, free polyatomic ions. Okay, so that means we're going to have IO3 is the polyatomic ion, its charge is negative, and this is aqueous. Now, what about the 2 there? Well, the 2 is telling you that when this dissolves, it's going to break down to 2 of these ions, so that requires a coefficient of 2 right there, and that is your chemical equation for the dissolving of calcium iodide. Okay? So, that brings us then, this is the result that I've got here. And again, as you can see, the dissolving reaction involves the use of the periodic chart and the polyatomic ion chart. And again, I have lots of polyatomic ion charts in class, so you can pick one of them, or you can just look off of one that you have in your Google Classroom. And again, make sure you put the phases on there, just like a regular equation we've always done. Phases are important. And go from there. So, now, those are ionic compounds. So what happens if it's not an ionic compound? Well, that's what this next one's going to be. This is called dimethyl ether. Okay? And dimethyl ether is a very water-soluble substance because of the oxygen. If you have oxygen in something, it's most likely going to be quite soluble in water. So let's take a look as to how we show the representation of that dissolving and how it's different from the ionic compounds. So it's a liquid. It's a highly volatile liquid. It catches on fire real easy. It does other weird things that concern scientists, as I found out when I was a student at McMurray College. We're going to dissolve this in water, so we'll put our arrow there and the H2O above it. Now, is this compound ionic or covalent? Well, obviously it's covalent because I introduced it as, oh, by the way, this is a covalent. But how would you know it if I didn't tell you that? Well, you look at this compound and see that there are no metals. Every single one of these elements is a non-metal. In other words, it lies to the right of the staircase of the periodic chart. Which means then, there will be no ions. So this makes this super easy to figure out. This is not going to break down. In fact, the oxygen is going to attract the water via this hydrogens, like I showed you with the chlorine, or the chloride ion being attracted by the hydrogen part of the water. And you're going to have water bombarding this oxygen to pull it away from the rest of the dimethyl ethers, because they are found, all substances are found clumped together, with the exception of gases. Gases are individual, but if they're in liquid or solid form, they're all clumped together in some fashion. So it's important that the water molecules, which are also bonded together, break apart. It's also important that the solute molecules, whatever they are, break apart, or the ions break apart, and that happens when the two collide with each other. So you have one collision creating two separations, one of solute, one of solvent, and then the free solute and solvent stick together. So in this case, collision occurs, but the entire molecule gets pulled away from the rest of the molecules to leave it as CH3OCH3. But instead of being liquid, because this is dissolved in water, using the Latin word aqua for water, we use aqueous as the phase. And that is all you have to do. So you have to identify first, this is so important, ionic or covalent compound. That is going to give you the direction that you need to go to figure out how you want to end up with your products. Do I get pieces or do I get the entirety? Pieces if it's ionic, the entirety if it's covalent. Okay, so that leads us up to then your practice problems. There are 5 of them. First thing you need to do is to determine the following compounds that I have listed here, are they ionic or covalent. Then I want you to give the dissolving equations for each one. So 2 answers each practice problem. Have fun!